Hello all, a very good day to all of you. So in this session, we will discuss all the questions that have come from analog circuits in 2018 GATE examination for electronics and telecommunication branch. Okay, so in 2018, there are 7 questions, right? 3 are of 1 mark and 4 are of 2 marks. So total 11 marks have been asked from this particular subject. Okay, so let us solve all of them one by one. Okay, so the first question is little interesting one. Two identical NMOS transistor M1 and M2 are connected as shown below, right? Okay, the circuit is used as a amplifier with input connected between gate and source terminal. So input is connected between these two. Okay, right, and the output is taken between drain and source. So this is my output. Okay, so here between these two terminal, I am taking my output. Fine. Okay, V bias and VD are adjusted so that both transistor M1 and M2 are in saturation. Okay, so we know for a transistor to be act as amplifier, it should be biased in saturation, right? So that is done by V bias and VD. Okay, and the transconductance of the combination, okay, of the whole combination, okay, is given by GM is equal to dID by dVGS. This is my current ID. Okay, this is I am applying VGS. Okay, so dID by dVGS is my transconductance, nothing but the change in output current by the change in input voltage. Okay, and the output resistance of the whole combination is given by dVDS by dID. So if I change some output voltage, how much my current change, that will determine my output resistance. Okay, but ID is the current flowing into the drain of M2. Okay, let GM1 and GM2 be the transconductance of M1 and M2, and R0 and R02 is nothing but the output resistance of M1 and M2. Okay, so with this information, what it is asking, estimate the transconductance and output resistance of this combination, right? So we have to find out the overall transconductance and overall output resistance. Okay, so let us go one by one. So first thing is, you see, if we apply a signal gate to source, right? This is VGS, right? Then we know, depending upon my input signal, there will be ID in transistor M1. The ID will be, okay, the transconductance of transistor M1 into the input AC VGS, right? Since M1 and M2 are connected in series, the same current will flow through here also. So the same ID will flow here. The whatever ID will flowing in M1, same will flow through M2 because both are connected in series. So the final ID is equal to GM1 into my input AC VGS. Okay, so if I want to know what is my ID by VGS, right? This is nothing but my GM1 only, right? So the output current ID here divided by my input AC voltage is transconductance of my transistor M1 only. Okay, so here dID by dVGS is nothing but transconductance of M1. Okay, this is the first solution. So GM is equal to GM1 only. So maybe C or D, right? C or D. Let us now calculate the output resistance. Okay, so for calculating output resistance, okay, since first we have to do the AC analysis, right? For AC analysis, what you have to do? I have to replace D bias by short circuit. For when we are interested only in the increment, I will replace all the DC supplies to short circuit. Okay, so let us build the equivalent AC equivalent circuit. Okay, okay. So in this, we have to, this is my source. Okay, so this is should be connected to ground. Okay, since I am interested in calculating the output resistance, so I will apply a small voltage called Vx, and if I want to find out Ix, okay, that will tell my output resistance. Okay, so for that I have to ground, gate and source also, because I am just applying a voltage at the drain, and if I can know Ix, then Vx by Ix will give me my output resistance of the overall amplifier. Okay, so this is M2, this is M1. Also, we know one thing, yes. So what you know is the resistance looking to the drain of M1 is nothing but R01, right? The resistance looking drain of the M1 is R01. So let us replace it by, I have a transistor. Okay, this is M2. I am looking to the drain of M1, so I can replace it by a resistance R01, right? Here this is grounded, and I am applying a voltage Vx. I am interested to calculate a current Ix. So Vx by Ix will give me my output resistance. Okay, now we'll apply the small signal equivalent model. Okay, so let us apply. So gate is grounded, right? This is my gate of M2. Okay, then source is also, this is my source of M2. Okay, this is G2, this is S2. Between source of M2 to ground, I have a resistance R01, right? And between gate and source, what I am having, GM2 into VGS2, right? Then what I have is between drain of M2 to source of M2, I have resistance is, that is nothing but R02. Then this is a voltage I am applying Vx. The current here is Ix. Okay. So now we will calculate the Vx by Ix here. So you can note it down here. If Vg is grounded, whatever current Ix is flowing, it will divide between these two. Again, the same current will flow through R01. So VGS2 is nothing but Vg2 is 0 minus Vs2. Vs2 is nothing but current Ix into R01, right? So VGS2 is equal to minus Ix into R01, because the total current Ix will flow through R01, and so S2 will be minus Ix into R01. Okay. Now we will apply a KVL in this equation, in this loop. Okay. If we apply a KVL in this loop, what it will be? It will be Vx minus, what is the current in R02? Ix is coming and going is GM2 VGS2. So minus the current in R2 is R02 is Ix minus GM2 into VGS2. Current into resistance is the voltage R02 minus Ix into R01 is equal to 0. Okay. So this implies Vx minus Ix minus GM2 and VGS2. So GM2 and VGS2 is nothing but minus Ix into R01. So it will be plus GM2, VGS2 is Ix into R01, okay, into R02 minus Ix into R01 is equal to 0. Okay. This implies Vx, okay, minus Ix, if I take it common, okay, it will be R02 plus GM2 into R01 into R02, okay, plus R01 is equal to 0, right? So Vx by Ix is equal to Vx by Ix is equal to nothing but my R0 is nothing but R0 is nothing but my overall output impedance of my combination looking from the D terminal. Okay, so it is equal to R01 plus R02 plus GM2 into R01 into R02. Okay, and since GM2, R01 and R02 is very large compared to R01 and R02, I can approximately say R0 is equal to GM2 into R01 into R02. Okay, so this is my answer. We will see GM2, R01, R02. So this is the answer, right? The overall transconductance is nothing but transconductance of M1, and the overall output impedance is nothing but GM2 into R01 into R02. Okay, here we concluded. Simply we have to replace with its AC equivalent model. Then simply we apply a KVL. If we apply a KVL, you will get a link between Vx and Ix. Then you can know what is the output resistance looking from the terminal D. Right? So this is the solution. Let's go to the next question. So in this question, in the circuit shown below, right, the op-amp is ideal. Okay, what is ideal op-amp, guys? Gain is equal to infinity, R input is equal to infinity, bandwidth is equal to infinity, output resistance is equal to 0. Right? This is ideal op-amp. And Zener diode is having a voltage of 2.5 volt. Right? At the input step, then we have applied a unit step voltage, right? We have applied a unit step voltage. So applied is V in equal to UT, right? A unit step voltage. Also at T is equal to 0, the voltage across each capacitor is 0, right? So this is the question. So this is a very nice question. So first attempt is, we will know कि since there is a feedback from output to input, the transistor is operating in negative feedback. So there is a principle called virtual ground, which says the voltage at the negative terminal is equal to voltage at the positive terminal. So in this case, since positive terminal is 0, so here also it is equal to 0. Right? This is the first step, step 1. Second step is, since voltage here is 0, the current here is I in. Okay, when I apply 0 unit step voltage, I apply 1 volt, right? 1 volt. So the current here is 1 volt by 1K. So the current I in is equal to, second step is I in is equal to 1 volt by 1K is equal to 1 milliampere. This is the second step. Third step we need to understand is what? The Zener diode, okay, is a 2.5 volt Zener diode. So we have to know what is the characteristic of a Zener diode. So this is Vz, this is Vz, this is Iz, right? So we know a Zener diode always operate in reverse bias. Since there is no minimum current is given for the breakdown, so we will assume that minimum current is 0, right? So up to when you go on increasing the reverse bias voltage across the Zener diode, the voltage will go on increasing with the zero current. When the reverse bias voltage reach to 2.5 volt, it will break down, then it will remain constant. Okay, whatever current you flow through the diode, Zener diode, the voltage across the Zener diode will remain constant, and it will act as a voltage regulator. When my voltage across the Zener diode in reverse bias is little bit exceeding to 2.5 volt. So up to 2.5 volt, whatever voltage you apply, that voltage will go on increasing with zero current. Then it will break down. Then it will allow the current to flow, and it will maintain the voltage 2.5 volt constant. Okay. So with this understanding, let us solve the question. See, so initially both are 0 volt, right? 0 volt. Okay, and what it is asking is, we have to calculate the time in a millisecond at which my output crosses minus 10 volt. Okay, so what is the output here, guys? This is 0 volt. This is C1, this is C2. Okay, this is VC1, this is VC2. Right? So what is the output voltage? V output is equal to 0 volt minus VC1 minus VC2. Okay, so output is equal to VC1 minus VC2. So my output voltage should be reaching to minus 10 volt. Right? So the voltage across C1 and voltage across C2 should be reaching 10 volt. Then my output will cross minus 10 volt, right? It is equal to minus of VC1 plus VC2. So the sum of voltage across C1 and C2 should be 10 volt to get my output reach to minus 10 volt, right? This is the first thing. Okay. So you see, initially the capacitors are uncharged. So there will be a current flowing, okay, 1 milliampere. Already we shown in this here. IN is equal to 1 milliampere. Now the total 1 milliampere will flow through the capacitor C1 because since the transistor is ideal, op-amp is ideal, there is no current into the negative terminal. So whole of 1 milliampere will flow through capacitor C1. Okay. Now since the voltage here initially 0 volt, so the diode is reverse bias. Okay. So up to reaching 2 volt, right? There will be no current to the generator. So whole of 1 milliampere will flow through my capacitor C2. Okay. So voltage of C1 and C2 will go on increasing. Okay. So initially, suppose 0 to T1. Okay. What will happen? The whole 1 milliampere will flow through. What is T1? T1 in the volt. T1 is the time when my VC2 will be 2 volt. Okay. So 0 to T1. Okay. 0 to T1. What will happen? At T1, my VC2 will be 2.5 volt. So what will happen? Initially, up to 0 to 2.5 volt, what will happen? You see, since my voltage across generator will be increasing up to 0 to 2.5 volt with zero current, so whole 1 milliampere will flow through C1 and C2. C1 and C2 means 1 ampere will flow through like this. There will not be any current through generator because up to 2.5 volt it reaching, the current is 0. So the whole current will flow through C2. So both C1 and C2 will charge with 1 milliampere current up to VC2 reaches 2.5 volt. Okay. So up to VC2 is equal to 2.5 volt, right? Both C1 and C2 will charge with 1 milliampere of current. Fine. Now what will happen? When it reaches 2.5 volt, the generator will break down. Right? Generator will break down. The voltage across generator will remain constant. After reaching 2.5 volt, voltage across generator will remain constant. Then what will happen? Then this VC2 will not charge because this VZ will break down. It will maintain the voltage 2.5 volt. Okay. So whatever 1 milliampere flowing will flow through generator now. Okay. So at T greater than T1, the 1 milliampere will flow through VZ because VC2 will remain 2.5 volt as generator will break down. Right? So at T greater than T1, 1 milliampere will flow through VC1 continuously, right? So then VC1 will go on charging from 2.5 volt to more, but VC2 will remain 2.5 volt. Then VC1 will go on increasing, right? Then when VC1 will reach 7.5 volt, then at that time VC2 is already 2.5 volt. Then VC1 plus VC2 will be 10 volt, right? So we have to calculate at what point my VC1 will reach 7.5 volt, because when my VC1 will reach 7.5 volt, already VC2 is 2.5 volt charged from 0 to T1 only. From 0 to T1, VC1 will charge to VC2 will charge 2.5 volt, and at the same time VC1 also 2.5 volt. Because same current is flowing, right? Same 1 milliampere current is flowing, equal 2.5 volt. From 0 to T1, VC2 will be 2.5 volt and VC1 also will be 2.5 volt. After T1, what will happen? VC2 will remain stop, VC2 will remain 2.5 volt only because generator will break down. Then VC1 will go on increasing, right? When it reaches to 7.5 volt, then the total output will be VC1 plus VC2 minus here. So it will be, so V out will be equal to minus VC1 plus VC2 is equal to minus 10 volt. Right. So we have to calculate the time, okay, when VC1 is reaching 7.5 volt. Okay, if I know the time when my VC1, when the capacitor 1 is going to 7.5 volt, at that time my V out will be VC1 plus VC2 will be 10 volt. Okay, so now our aim is to calculate the time required by the capacitor C1 to reach to 7.5 volt. Okay, so how to know VC1 equal to 7.5 volt? Okay, I want to know the time when it reaches 7.5 volt. Okay, so my aim is to calculate the time for the capacitor C1 to go to 7.5 volt, and the current IN is flowing 1 milliampere only, right? So IC1 also is equal to 1 milliampere. We know IC is equal to C dV by dt. This implies 1 milliampere is equal to C is nothing but 1 microfarad, dV is nothing but 7.5 minus 0 time t minus 0. So t is equal to 0, current started flowing. Okay, so this implies time t is equal to 1 microfarad into 7.5 divided by 1 milliampere is equal to 7.5 millisecond. Okay, so at t is equal to 7.5 millisecond, my VC1 will reach to 7.5 volt, VC2 is already reached to 2.5 volt. Okay, then my V out will be minus of VC1 plus VC2 is equal to minus 10 volt, right? So the answer should be 7.5 millisecond. Okay, I think it is clear to all of you. A good trans impedance amplifier should have what? Input impedance and output impedance. What is the condition of input impedance and output impedance? So what is a trans impedance amplifier? Trans impedance means output voltage by input current. Okay, an amplifier which takes my input current and convert it to give my output voltage, then that I can call as a trans impedance amplifier. Trans means output to input. Impedance means output is voltage, input is current. Okay, so here you understand. Trans means output to input. Impedance means output is voltage, input is current. This is very important. So if we have a trans impedance amplifier, it is, suppose I have a current source, right? IS, I have some resistance RS, right? This is applied to a amplifier, okay, which is trans impedance. Okay, right? What did it do? It should accept the current, right? Should take as much current as possible from the source. So the R in is here, and it gives a output voltage which is a impedance, you can say R into the current I in. This is my I in, and it delivers a, it is a output impedance R0. Okay, then it gives to the load RL. This is my output V0. Okay, so what a trans impedance amplifier does, it takes a current from the current source IS, input current IN, then this IN is get converted into a voltage depend upon my trans impedance is nothing but here R into RIN, then it delivers the voltage to the output. Okay, so what we want is the whole of current IS should flow to the input, right? Then the RIN should be very small compared to RS. Then only the total current is will flow through my Rin. So the input resistance should be low. And what I want, whatever output voltage is nothing but R into In should go completely to RL. So what I demand is R0 should be very less compared to RL, because then only whatever voltage is there developed R into In will deliver to my output RL. Okay, if R0 is more, then it will drop across R0, right? So I want my R0 to be very small. Okay, so R0 also should be low. Okay, so low is the answer. Answer should be D, right? Let's see the next question. So in this question, the circuit shown in the figure is used to provide a regulated output voltage 5 volt, right? 5 volt across a 1 kilo ohm resistor, right? Load is 1 kilo ohm. Okay, so assume that the diode has a constant reverse breakdown voltage for a current starting from minimum to a maximum allowed current, right? Then the input voltage is varying by 5% from its nominal value 6 volt. Okay, what it is asking, the range of the resistance of the diode in breakdown region is negligible. Okay, that's okay, it's kind of the ideal diode. Okay, then we have to find out the value of R and the minimum required power dissipation rating of the diode. Okay, so what you have to find out, for this application, which kind of diode I should choose, means what is the minimum power dissipation of the diode. Okay, we have to choose a diode. So I have to choose a diode with what power dissipation. This you have to calculate. Also, you have to find out what is the value of R, so that this zener will be operating as a voltage regulator when my input is varying by 5% from 6 volt. Okay, so when my input is varying, what is the value of R, that will ensure that zener is regulated. That is the first condition. Second thing, what it is asking is, you have to calculate the minimum power required power dissipation rating of the diode. Okay, this is a very simple question. Okay, so first thing you have to calculate the value of R. Okay, so let me tell you a little briefly. The zener is IZ and VZ. So it operates in reverse bias, right? So what happens, when the reverse bias across zener will go on increasing, there will be very small amount of current. Okay, then after a certain amount of reverse bias, it get breakdown. Okay, then the voltage remain constant. It behaves as a voltage regulator. When the voltage started constant, right, the current at that time moment is called I-knee, right? I-knee. Let's take another color. Current at this point is called I-knee. I-knee. And depending upon the maximum power rating, this should be I-max also. I-max. Okay. So, in other words, my zener to be operating as a voltage regulator, my minimum current flowing through the zener should be I-knee, and the maximum current should be I-max. So, my current in zener diode should be ranges between I-knee or I-minimum, I-knee, or it is called, or I-minimum to I-maximum. Then only I will ensure my zener will be operating as a voltage regulator. Okay. So the first condition is, okay, let me change my color. Okay, the current in zener IZ should be, okay, greater than equal to I minimum, right? IZ, what I want, the minimum current to the minimum IZ minimum, okay, should be greater than equal to I knee. Okay, here knee nothing but minimum current is given how much, 2 milliampere. IZ minimum is 2 milliampere. Okay, so what is IZ minimum? IZ minimum is nothing but this is my current IS, this is my current I load. Okay, so I source minimum minus I load maximum will give me my IZ minimum should be greater than equal to 2 milliampere, right? Given 2 milliampere, right? What is the I source minimum? Source minimum is V1 minimum minus Vz by R minus what is the IL maximum? Since load is not varying, load is constant, so I will take Vz by 1K. If because here the load is not varying, IL max is equal to IL minimum equal to IL nominal also. See, the load is constant here. Load is constant, so I take Vz by 1K that is equal to 2 milliampere. Okay, this implies V in minimum is nothing but 6 volt and 5% variation. That means 6 volt into 0.95. It can go towards the downside. Minus 5 volt is the general diode. By R minus 5 by 1K that is equal to 2 milliampere. This implies R should be less than equal to 6 into 0.95 minus 5 by 2 plus 5 is 7 milliampere. Is equal to, you have to calculate the value using a calculator. Okay, so 6 into 0.95 minus 5 divided by 7 milliampere give you how much it gives you? 100 ohm. Okay, so 100 ohm is there in the answer? Yeah, 100 ohm there. Maybe C or B is the option. Okay, so what you have to do? IZ minimum, you know, 2 milliamp. What is the IZ minimum is source minimum minus load maximum will give me my IZ minimum. Then since load is constant, so I put a constant load. Then I got R is equal to should be less than equal to 100 ohm. Okay, R should be less than equal to 100 ohm, right? So I put 100 ohm. Second thing is I have to know the IZ maximum, right? We know the IZ should be less than equal to IZ maximum. Okay, what is the maximum current in the general diode? Is nothing but the maximum current in general diode is nothing but given by IS maximum and I load minimum. Okay, so I source max minus I load mean giving my the general diode maximum current. Okay, what is I source maximum is V1 max minus Vz by R minus I load minimum. Since the load is constant, I will put Vz by 1K only should be less than equal to IZ maximum. Okay, so what is V1 maximum? 6 volt into 1.05, right? It can go up by 5% minus 5 volt divided by R already we calculated is 100 ohm, right? Minus 5 volt by 1K should be less than equal to IZ max. Okay, so let's use the calculator, guys, and let me know what is the IZ maximum. The maximum is nothing but 6 into 1.05 minus 5 divided by 100 minus 5 by 1K. 5 by 1K. I got 8 milliampere. So this implies IZ max should be less than equal to 8 milliampere. Since the maximum current is should be less than equal to 8 milliampere, what is the rating of the diode? The rating of power rating is equal to power rating, minimum power rating. Okay, minimum power rating is equal to IZ max we need into Vz is equal to 8 milliampere into 5 volt is equal to 40 milliwatt. This is the answer. So thing is, I want a general diode which can support maximum of 8 milliampere current. For supporting this, I need the power rating of 40 milliwatt. So answer is 140 milliwatt is answer B. Right? B is the answer. Let's see the next question. So a DC current of 26 microampere flowing through the circuit given, right? The diode in the circuit is forward biased and it has a ideality factor of 1. That is good. 8 quotient current, right? Quotient means DC current, right? The diode has a junction capacitance of 0.5 nanofarad and it is its neutral resistance, its neutral region resistance can be neglected. Okay, that's right. Okay, then assume the room temperature thermal equivalent voltage is 26 millivolt. The frequency omega is equal to 2 into 10 power 16 6 radian per second. The amplitude of this small signal current in a diode. So we have to calculate. So what is asking? See, there is a DC current. Okay, before application of this voltage, there is a DC current flowing. Okay, IDC is flowing in the circuit. That is nothing but is equal to 26 microampere. Okay, when we apply a signal 5 sin omega t millivolt, then there will be a AC current that will flow through the same path. It will be equal to how much? It is asking. So the I total will be IDC plus IAC, right? So I have to calculate the magnitude of the amplitude of the small signal current of diode. Okay, so for this we have to what we have to do? We have to replace the small signal equivalent circuit. Okay, so let us replace it by small signal equivalent circuit. The DC voltage will be short circuited, right? Because I am just interested in I am interested in finding the small signal AC current, right? For that, I am making the DC voltage to 0. Then I will replace it with its small signal equivalent circuit. Okay, the small signal equivalent circuit of AC will be AC only. For the DC voltage, it should be sorted. Okay, sorted. Then I have a ground. Then the diode. Okay, what is the small signal equivalent of a diode? Okay, diode will be, it is equivalent of a capacitance in parallel with a resistance, right? Then I have a 100 ohm. Okay, so this capacitance is nothing but C diffusion plus C depletion. Okay, so diffusion comes because of when the diode is forward biased, there will be charge injection. Then because of that, there will be a capacitance that is called diffusion capacitance. And the depletion capacitance is nothing but when in a PN junction diode, in the junction there is a depletion region. So there is a capacitance because in the depletion region, in N side I have positive charge, in P side I have negative charge. So it gives a capacitance called C depletion, and it is given in the question. The C total is equal to 0.5 nanofarad. 0.5 nanofarad. So C is given 0.5 nanofarad. What is R diode? Okay, you know R diode is equal to the thermal voltage by the DC current flowing through the diode. Okay, so the resistance, the small signal resistance will depend upon the DC or quotient current that is flowing through the diode before application of AC voltage. Okay, because you see why I am telling you just briefly. This is the diode current, right? So this is ID, this is VD, right? So if you want to small signal current, right? Suppose we are here. Let me change the color. Okay, suppose we are at this point and this is the DC current. Okay, at this point the resistance will be something. Suppose you go to here, suppose we are here, and at this moment the resistance will be different. So the small signal resistance will depend upon what is the quotient current that is flowing. Okay, that's why my small signal resistance is nothing but Vt by Id. Okay, equal to 26 millivolt is given, Id is given 26 microampere, right? Id is given 26 microampere is equal to 1 kilo ohm. Okay, right? So what is the impedance of my capacitor? The xc is equal to 1 by j omega c is equal to minus j by omega c. Okay, omega is how much, guys? Omega is 2 and 10 power 6, 2 into 10 power 6 into c is 0.5 10 power of minus 9. So 6 9 is 3. You got cancel is equal to minus j into 1000. Okay. So this is my v in 5 sin omega t is equal to v in. Okay. So now I have to know the resistance of this, the impedance of this path. This impedance of this path is equal to x is equal to x is nothing but impedance of the diode. Okay, diode is equal to RD parallel to XC. Okay, is equal to RD is 1000 ohm. Okay, into XC. XC is nothing but minus J into 1000 ohm divided by 1000 plus minus J into 1000. Okay, then both are connected in parallel. RD into XC by RD plus XC. Okay, so 1000 get cancel. So what I got is 1000 into minus J, right, divided by 1 minus J, right? So X is equal to 1000 into minus J by 1 minus J. So I will multiply 1 plus J, and here also I will multiply 1 plus J. Okay, so equal to how much you will get? Minus J into 1 plus J into 1000 divided by 1 square minus J square is 2, right? So 2 get cancel. So I got is equal to 500, okay, into minus J into J square. So it is plus 1. Okay, minus J into J is minus J square. J square is minus 1. So I got plus 1. So this is equal to 500 minus 500 J is the impedance of X. So what is my current? Current is what is the total resistance? Total impedance. Total impedance is nothing but X plus 100 ohm. So total impedance Z is equal to X plus 100. So 500 plus 100 is 600 minus 500 J. So if I want to calculate the small signal current ID amplitude, it should be V in amplitude by Z magnitude. Okay, V in magnitude is how much, guys? Is 5 millivolt. Okay, is 5 millivolt by this is nothing but 600 square plus 500 square. Okay, so if we will take a calculator and do it, 5 millivolt, 5 into 10 power of minus 3 divided by root over of 600 square plus 500 square. I got 6.401 microampere is equal to 0.401 microampere. Okay, so this is a very easy question. First thing you have to understand is what is the small signal equivalent of a diode? Nothing but a capacitor in parallel with a resistor. The resistor value depend upon my DC or quiescent current. Here it is 1 kilo ohm, and the Xc is nothing but 1 by j omega c. Both are in parallel. Simple calculation. You have to get the impedance of the diode. This is impedance of the diode. Okay. Then the total impedance is equal to impedance of diode plus 100 ohm. Then ID is nothing but V in magnitude by impedance magnitude. Okay. This is give me my the magnitude of my current ID. Okay. So the ID current will be 6.4 microampere equal to 6.4 microampere. Okay. Then go to the next question. So in this question, an op-amp is biased in the circuit as implemented as shown in below. Okay, right? In the above circuit, assume the op-amp to be ideal. Already I discussed what is the ideal diode. Okay, the voltage of the node A, okay, is how much? Okay, so guys, we see the first attempt is, since this there is a feedback from output to input, it is a negative feedback because of virtual ground. Okay, the A should be 0, right? Because of virtual ground. But since it asked the calculate the voltage at VA, then should be little cautious. Okay, so when VA is equal to 0 because of negative feedback, what is my V output? V output is equal to minus R2 by R1 into 1 volt is equal to nothing but minus 31 by 1 kilo into 1 volt is equal to minus 31 volt. Okay, so if we will assume virtual ground, that is VA is equal to 0, then we'll get a voltage minus 31 volt. But you see, since in this circuit given, the supply voltages are limited to plus 15 and minus 15. So my V output cannot never go to minus 31. It will be limited to minus 15 volt. So it will be saturated to minus 15 volt. So in this case, when my V out will be saturated, then my VA will be changing, because here when we assume VA is equal to 0, I am getting minus 31 volt because of virtual ground principle. But since the supplies are limited, it will be limited to minus 15 volt. Then in that case, definitely my VA have to be changing, right? Then we have to calculate what is my VA. So we know my output will be VO is equal to minus 15. Already you know, because it is saturating to minus 15 is equal to minus 15. Then we will apply a nodal potential here. So VA minus 1, right, by 1K plus VA minus 15 means plus 15 by 31K is equal to 0. This implies VA minus 1 plus VA plus 15 is equal to 0, right? This implies VA is equal to 2VA is equal to 14 minus 14, right? So VA is equal to minus 7 volt. Okay, VA is equal to minus 7 volt, right? Minus 7 volt. So for making my V output minus 15 volt, my VA have to change to minus 7 volt. Then because when VA is equal to 0, my output should be minus 31. But I cannot go to minus 31. It is limiting to minus 15. So for making minus 15, I need a voltage of minus 7 volt at node A, right? So this is the answer. Okay, because you see the input current when it A is 0, 1 milliampere, it is flowing through the 31 kilo ohm resistor, giving me 31 volt, minus 31 volt, but not possible. So my VA have to change so that I will get minus 15 volt. Okay, so this is the answer, is minus 15. Minus 7 is the answer. Okay, so VA is changing to minus 7 volt to get minus 15 volt at the output. So then in this question, in the circuit shown below, right, the W by L of M2 is twice that of M1. Okay, W by L of M2 is equal to 2 times the W by L of M1, right? The two NMOS transistors are otherwise identical, right? Two are identical. Okay, the threshold voltage VT of the transistors are 1 volt, right? 1 volt. Note VGS for M2 is should be greater than 1 volt. So what is given, right? First condition is the W by L of M2 is twice of M1, and the VT of transistors are 1 volt. Both are having 1 volt, and it is giving the condition that my VGS of M2 should be greater than equal to 1 volt. This is given the condition. Okay, and the current in NMOS transistor can be modeled as ID is equal to this one and ID will this one, right? If VDS is less than VGS minus VT, That means it is in, when my transistor is in linear region, this is the current. When my transistor is in saturation region, this is the current. This already we know, right? So with this condition, I have to calculate the voltage at X. Okay. So the most important point in order to solve the circuit is we have to know what is the condition of M1 and M2. What I mean is my M1 is in linear or saturation, and my M2 is linear or saturation. That we have to determine. If we determine what is the condition of M1 and M2, I can put the current equation like this. Then I can calculate the current, calculate the voltage Vx. Okay. So first see for M2. For M2 is given VGS of the M2 is greater than 1 volt. Okay. VGS of M2 should be greater than equal to 1 volt. Greater than 1 volt. Okay. Not equal to. Okay. VG of M2 is 2 volt, right? 2 volt minus VS2 should be greater than equal to 1 volt, right? This implies 2 minus VS2. This is source 2, right? So source 2. This is drain 1, right? So source 2 is nothing but Vx should be greater than equal to 1 volt. This implies Vx should be less than 1 volt, right? Vx should be less than 1 volt. Now we will determine the condition of this one. Okay. What is VDS2? VDS2 is equal to 3.3 the drain 2 minus source is less than 1 volt. 1 volt. This implies VDS2 is 3.3 minus 1. So should be greater than equal to 2.3 volt. Right? If Vx is less than 1 volt, then 3.3 minus less than 1 volt should be greater than equal to 2.3 volt. So VDS2 is greater than 2.3 volt. What is VGS is given greater than 1 volt, right? 1 volt, and VGS should be greater than 1 volt, and VGS minus VTH is equal to should be greater than equal to 1 minus 1 equal to 0 volt, right? Because okay, VGS2 minus VTH should be greater than equal to 1 volt is VGS2 minus 1 volt is the VTH2 should be greater than equal to 0 volt. So you see the condition is meeting, right? VGS minus VTH and VDS. So VDS is greater than VDS2 is greater than VGS minus VTH, right? VDS is greater than VGS minus VTH for transistor M2, right? VDS2 is 2.3 volt, VGS minus VTH is greater than 0 volt. So it is meeting the condition of VDS greater than VGS minus V2. So the transistor is operating in saturation. So M2 is saturation, right? We have to apply this equation for the current. Okay. Then for M1, for M1, okay, it is given the Vx is nothing but VD1, this is drain 1, this is source 1. Okay. VD1 should be less than equal to 1 volt given. So VD1 is less than 1 volt. Implies source is grounded. So VDS1 is less than 1 volt. Right? This is one condition. Then VGS1 is 2 volt minus 0 is 2 volt. Implies VGS1 minus VTH is 2 minus 1. 2 minus 1 is equal to 1 volt. So you see, VDS1 is less than 1 volt and VGS1 minus VTH is equal to 1 volt. That means VDS1 is less than VGS1 minus VTH, right? Since VDS1 is less than 1 volt, VGS1 minus VTH is 1 volt. That implies VDS1 is less than 1 volt. VDS1 is less than VGS minus VTH, right? This implies this condition is satisfied. So the current for the transistor M1 is like this, and it is in linear, right? And we know whatever current flowing through transistor M1, since they are in series, the same current flowing through transistor M2. Okay, we know IM1 is equal to IM2, right? What is IM1? IM1 is linear. Okay, VDS1 less than VGS minus VTH, so it should be like this one. Okay, IM1 is mu1 Cux double by L. Okay, double by L. VGS minus VTH. VGS1 minus VTH1 into VDS1 minus VDS1 square by 2 is equal to half mu1 Cux double by L of M2, here it is M1, right, into VGS2 minus VTH whole square, because for M2 we have to apply this equation, right. Now we have to find out, simplifies, double by mu1 Cux get cancelled, right. Double by L of M1 is M2 is, so M2 is twice of M1, okay. So double by M of M2 is twice of M1, so I can put double by L of M1, let us put it. VGS1 is nothing but 2 minus 1, 2 minus 1 into VDS is nothing but Vx minus Vx square by 2 is equal to half double by L of M2. And VGS2 is nothing but 2 minus S2 is Vx minus VTH. VTH is equal to 1 full square. So this is double by L1 is M2 is twice M1. So this is equal to, this is nothing but 2 into double by L1 of M1. So the 2 get cancelled. Simplifies. This double by L1, this is get cancelled. I will apply 2 into double by M1. So I will put 2 minus 1 means equal to Vx minus Vx square by 2 is equal to 2 get cancelled, 2 minus Vx minus 1 whole square. Okay, this I have to solve to calculate Vx. Okay, let us solve it. Simplifies. Vx minus Vx square by 2, Vx minus Vx square by 2 is equal to 2 minus 1 is 1, 1 minus Vx whole square, right? Fine. Simplifies. 2Vx minus Vx square is equal to 2 into 1 plus Vx square minus 2Vx, right, is equal to 2Vx minus Vx square is equal to 2 plus 2Vx square minus 4Vx. Okay, everything will take one side. Okay, 2Vx square plus Vx square is 3Vx square minus 4Vx minus 2Vx is equal to minus 6Vx. Okay, plus 2 is equal to 0. So let us take a calculator and solve it. Go to calculator equation. You should shift to mode. Equation is 5. X square is 3. So I put 3 minus 6. Then another is 2. Okay. So I got either Vx is equal to 1.577 volt or 0.4226 volt. Okay, so what it is given, Vx should be less than or equal to 1 volt, right? So this implies Vx is equal to 0.422 volt is the answer. Okay, so the important thing is we have to know transistor M2. For transistor M2, you have to apply this condition or this condition. Similarly, we have to know for transistor M1, I have to apply which condition. If I know the condition, then we have to equate the current, right? With the same current flowing through the transistor M1 and M2. Then if we equate the current, I can easily calculate the potential Vx. Okay, so I think that's all. Thank you guys for the patient listening.